All right, so take a minute to copy down this screen. If you feel like you need to pause it after I just talk through the different concepts we'll be looking at, make sure you do that and get this all copied down. Second derivative test is going to be similar to the first derivative test in that we will be finding, instead of the first derivative, the second derivative, and then setting that equal to 0. Instead of looking for where the graph is increasing, decreasing, and max and min points, we have two new concepts that we'll be looking at. First one is concavity. Concave up is when the graph is facing up. Concave down is when the graph is facing down, like the example is drawn here. And then the example at the bottom shows a graph that has both a concave up and a concave down piece with something called an inflection point. The inflection point is the point or points, if there's multiple, where the graph changes concavity. So if you look at the red piece, that piece is facing up. If you look at the green piece, that piece is facing down, and it changes right at that inflection point. So we'll take a look at a few examples. Again, if you need to pause to copy that down, make sure you do it. Again, second derivative test. Oops. We will have to find two derivatives, and we're going to set the second equal to 0. Again, this will find concave up, concave down intervals, kind of like the increasing, decreasing intervals, and also inflection points. So rather than max min points, the x values we get potentially are inflection points. We will have to check the positive negative to make sure that that's true. So we'll start off with an example, kind of like our first example with first derivative test, where it will be only 1 point by the time we get that second derivative. So we have x cubed minus x squared. Take the first derivative. We get 3x squared minus 2x. And then we'll take the derivative again. So an extra step here, not a terrible step because it will be something simpler than what you would have worked with for the first derivative. And we are always then setting it equal to 0. That is the key. That's going to get you either your max min points for first derivative test or your inflection points for second derivative test. If you solve that, we get x is equal to 1/3. Like we did previously, we will make a number line. So a lot of similarities between this and the first derivative test, and we'll test out some points again on either side to see, are we going to have concave up or concave down? So let's check something to the left of 1/3. Let's try 0. Again, remember 0 doesn't always work. And we're also testing this out in that second derivative. You're only plugging the 1/3 back into the original once we figure out if it's an inflection point. There's potential that it's not. And then also when we figure out the concavity. So if we plug in 0 to that, we end up getting a negative answer, -2. So we're going to say that that space is negative. And that's going to mean something about the original graph. And then we're going to do the same thing on the other side. We could do f double prime. I'm going to pick 1 since that's an easy one to plug in, and that comes out to be +4. So in fact, this other side is positive. And just like with increasing and decreasing, the negative and positive make sense for the original function. So if I now move on to the original function, if it's negative, f of x is concave down. Down and negative makes sense, they go together. And then if it's positive, the original function would be concave up. And then just to remind you, concave down. And then that definitely means there's an inflection point here, and then it's going to switch. This is not my best change over there. It's going to switch to concave up. So just like we did for the other ones, trying to draw that sketch in to see kind of an idea of what it will look like and then what we'll need for our intervals. We'll have an inflection point. So instead of saying the max and min points and the increasing, decreasing, we're going to say it's concave down. Actually, I put concave up first. It doesn't really, it will matter what order it's asked for you on the practice, from 1/3 to infinity, because the second derivative is greater than 0, which just is another fancy way of saying positive. That's always going to be the case. Up and greater than 0 will always match up. And then it's concave down from negative infinity to 1/3, because that's where the second derivative is negative. Again, we'll put less than 0, a fancier way of saying positive versus negative for those. And then for part C, we're going to do the inflection point. We'll do f of 1/3. And something you can do if you don't want to have to type the fraction in every time is, if we haven't already talked about this, we'll do alpha y equals and type in the 1/3. And then you can actually hit STO for store and store it in x. X is the kind of the function that we're working with. And then instead of typing in 1/3 cubed, you can type in x to the third minus x squared, since we have that 1/3 stored in there. Or you can type it in the regular way too. This might just save you a little bit of time. So -2/27. And then we're just going to write, we have an inflection point at, and this time we're going to write the entire point out. And the reason we do is because we have that change in concavity. So we only give our reasons for why that's happening. If the whole thing was concave up or the whole thing was concave down, that would not end up being an inflection point. So let's take a look at 2 more examples just to see some varying difficulty levels of these. Our second one is f of x is equal to x to the 4th plus 2x cubed. Now when you see this and you're thinking, oh, that's going to be my first derivative test, this one would be a little more challenging for sure, but we are doing the second derivative. So we'll get 4x cubed plus 6x squared minus 72x plus 60. We don't have to set that equal to 0 because we are doing the second derivative test. So if we take the second derivative, we get 12x squared plus 12x minus 72. And we're going to set that equal to 0. Now try to make things easier for yourself. I notice I have 12x squared and 12x. Does 12 go into 72? Then I can take out a GCF here, and it does. So let's take out that 12. And then we have something that's so much easier to factor. And you wouldn't set the 12 equal to 0 anyway, because that doesn't work. But you can always kind of test that out. So we end up getting 2 answers for x, -3 and 2, which makes sense for a quadratic, that we're now going to test out on our number line 3 different values to see if we get positives or negatives. You don't have to write down what you're checking every time. So let's say I want to do like f double prime of -4. This is another thing that's nice about storing. So if I do -4 and I store it in x, now I can say, I can type in I'll just type in the one that doesn't have the 12 in front because it doesn't really matter if I type that in. So I get 6. I get a positive answer, so I'm going to fill that in as positive. So although normally I write these down, it's not necessary. You just have to kind of do, okay, that's positive, picking something in between. This one's an easy one. If I pick 0, so here I did like f double prime of 4, came out to be positive. Then in the middle, I'm going to do f double prime of 0. That should give me -6. That's an easy one, so that's negative. I don't need the calculator for that. And then the next one hopefully comes out to positive, so we get another inflection point, but it might not. We'll do f double prime of 3. So the nice thing about using the calculator with the storing, if I now do 3 and store it in x, I go back up and grab the thing I already typed in, I don't have to retype it again. It'll replace that and give me my new answer of positive 6. So that is in fact positive. So you could still write out what you're testing. You don't have to write the number that it comes out to be. Again, you want to just write down, is it coming out positive or negative? And then, does that make my original function concave up or concave down? So I'm always going to write the derivative information on the top like you did with first derivative test, and then the original function underneath that. So this is going to go up, then down, then up again. This is talking about concavity. So I'm going to try to sketch this. Facing up, facing down, and then facing up again. So at each of those spots, we should have inflection points. It doesn't matter if they're actual max or min points. They usually are not. They're usually in between the max and min points. I kind of made one of them look like a minimum, but it shouldn't be. All right, so again, we're going to write down the different parts here. Concave up from negative infinity to negative 3. Union, because we'll have 2 of these, 2 to infinity. And again, because the second derivative is greater than 0, this reason will not change every time. You just have to make sure you find the correct concave up and concave down. And then it's concave down between negative 3 and 2 because the derivative is negative or less than 0. And then we have points of inflection. We'll get those by plugging in original function f of negative 3, which comes out to negative 447. I'm going to let you trust me on that. And then we're plugging in f of 2, and that's going to come out to 38. Again, if you want to store the answers in x, you would only have to type this really long function in once, and then you can go back and grab it to get your answers. So the points of inflection would be negative 3, negative 447, and 2, 38. And again, the reason is there's change in concavity. We'll just do one more because this is more of like a special case, just so that you can see what happens with this and how you would answer the questions, because it's possible to get a graph that's only one or the other. So I'm just going through doing all my derivatives. And then at the end, you would set this equal to 0. 12 does not equal 0, so no inflection points are possible. All right, so to write the answers for this, there's really no work left involved, just identifying a couple things. It's never concave up. So you'll notice there is a negative sign here. So that means it's always negative, the second derivative, which means can't be concave up. Greater than 0, or again, positive, if you want to write it that way. And that means it's concave down everywhere. So you would write negative infinity to infinity. And then also, I already wrote this, but there's no inflection points since the concavity doesn't change. This actually would be your favorite example to get, because there's really not much work involved. You don't need to do any number line checking. The only thing you just have to be careful of is if your answer comes out to be positive or negative. That's going to tell you whether it's always concave up or always concave down. Parabolas would make sense because if you think about what this graph would look like, a negative parabola only faces down. It has a maximum point, but it doesn't change concavity because it's always facing down. Positive parabola, same thing, would always be facing up. So it wouldn't have inflection points, would only have concavity one way or the other. All right, so that wraps notes for the second derivative test. You will now have a chance to try some practice that goes along with this.